Hello students, and I know it's summer, but I need to make a small clarification on a video I did. I think it was um, my videos on group theory and treating femboys as sets with some stuff. So treating them as groups, and from there, sort of um, proving that they are this, they are that, they're not this, they're not that. But I need to make an important um, clarification about how I treated groups. So, me before used to think that a set can be a group if that set has symmetries of an object or rotations we can apply on an object as its elements. So let's say that phi is an action that rotates this pencil, something like that, in any direction, and this is part of a set S. Then I immediately assume that S is a group. But the thing is, that's not what a group is, to be honest. Because there's a more rigorous definition for a group, a more general definition, wherein what I just told you is just a sort of special case of. So, what actually is a group? So here's a small lectures from Professor Femmy sort of thing, wherein I actually tell you the actual math behind what I discussed. An actual group, let's say I can zoom in, right? Yeah, I can zoom in. I'm using my phone right now. The ground is over, and I think I can do videos. I think I'll be able to make Femboy math videos, but I'm not sure if I really want to nowadays, considering that was the reason why I got grounded in the first place and I wasn't able to upload. But aside that, okay, going back to the topic. So a group G is a set N equipped with a binary operator dot such that for any two elements in N, A acting on the second element, or the first element acting on the second element, yields another element C, which is an element of N as well. I know this is a bit not well formed in the language of set theory. What we say not well formed is when we randomly just put quantifiers around, and that we don't really put all the quantifiers at the beginning. So what is a quantifier? A quantifier is something that specifies what you're talking about. So it tells you what this thing is and what are the conditions of it. So we're saying for all here, this upside down A, to say for all elements. So it applies for all elements inside N. So it applies for all A and B inside N. And so we're saying that any A acting on B, or any product of A and B, would yield a C, and that C would be part of N, right? And the elements of N satisfy these things called group axioms. Now, I've already discussed to you guys what axioms are so many times on this channel. You guys should already know it. But those who still don't know, axioms are fundamental assumptions in mathematics where we base everything off of. So they are sort of the bedrock of mathematics, and from there on, or rather they're the foundations of mathematics, is what most mathematicians refer to axioms as foundations of mathematics, where we build all our reasoning on top of. And there are these things called group axioms, which basically tell us whether, or give us a sort of criteria for whether a set with an operation is a group. Now, let's take for example the set of all integers: minus infinity, dot dot dot, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, dot dot dot, positive infinity. So the numbers ranging from minus infinity to positive infinity. So this interval over here, this is the integers, so which we denote as the capital blackboard bold Z. If we equip this with this binary operator, let's make a group G composed of Z, the integers, and this binary operator. Well, this group exists here, so we can construct a group of this with this operator, because if we multiply any two numbers here, the same number would appear inside this set, would be inside the set. So for example, if I were to multiply -3 and -2, we get +6. And +6 is somewhere here. It's right after 5. Doesn't mean I didn't list it, it's not there. It's really there. So basically, it's part of the set. So therefore, Z can equipped with the multiplication operator can be thought of as a group, or can be called a group. Now, the real way that we denote groups is via this ordered pair over here, which is saying we have n grouped with, so we basically pair up this set n, and a set could be any collection of objects, mostly mathematical objects such as matrices, numbers, could be graphs, stuff like that. And this operation over here, mostly the multiplicative or product operation, but we're talking about product here in the universal sense and not entirely the specific sense where we're multiplying two things together, like we're having n object and then we multiply it by a times we get n plus n plus n. No, that's not what we mean by this. This is a universal product, which is saying that this object acts on that object. Rather, this object, let's say we want two objects A and B to act on each other. The universal sense, or actually the specific case of multiplication, or thinking of product as a multiplication, is transitive. So we're saying that, well, A times B is equal to B times A, but in this case, this is not the same. This is not equal to B acting on A. Okay, so let's pretend that this charger is something I have, right? And then we were to think of A and B as rotation. So let's say that A rotates it this way, and then B sort of rotates it like this. Okay, so, or actually like this, let's do it like that. Okay, so we can think of A acting on B as doing this and then doing this. But that is fundamentally different than doing this, or like this, okay. Doing this and then doing this. It's fundamentally different. Okay, I'm gonna do it again. A doing this and then B doing this. Looks like that. But if we apply B first by rotating it, doing this and then doing this, it's totally different. So this is why these two are so different from each other. It also applies for when we multiply matrices together. So okay, I know it's gonna be a bit long. Maybe I might have to split this video into two parts. So let's say we have matrices A, B, sorry for my stammering. So we have first matrix A, B, C, D, and the second one E, F, G, H. This is not the same as E, F, G, H times A, B, C, D. All right. So we apply this rotation, this thing. Actually, it's this one first on our coordinate system. We stretch it. We stretch the basis vectors by EG and FH, or rather replace them by EG and FH as our new basis. So we first modify it like that, and then we modify it like this. So let's say that it stretches it like this, or every unit gets stretched like this, and then it sort of gets sheared, sort of does that, and then gets stretched like this. So like this. Alright, so first like this and then like this. It's fundamentally different if we were to do this first and then do this. Do this first and then do the second one, so which would be just stretching it like that. It would be different. So we did this first, we stretched it. Actually, here we did the shear first. We stretched it to the side first, and then we did this, but which is just scaling it. It's different from if we just scaled it and then did the shearing, which is like this. It gives us different results. And so that's why this acting on, or this product, universal product definition, is not really indicative of actual multiplication. And so, what are the group axioms? So, I'm actually using my notebook right now. Um, I'm using my notebook right now, and I'll just open the page, a bullet point, which tells us the group axioms. All right. So the first group axiom is that for any three elements inside G, which is our supposed group, A times B times C. So if we were to multiply A on B, or if we were to have A act on B, and then have that product act on C, it would be the same as having the product of B and C and having A act on that product. So it's commutative, you can say. And for any A in G, for any element inside G, there exists an element inside G such that if we were to multiply these two or have the product of these two, we would just get A itself. So it could be thought of as 1, it could be thought of as 0, such that the multiplication by 0 yields the number itself. This E is called the identity element. It's called the identity element because if we multiply by it, we get just that thing that we multiplied it by. And so, okay, for this third one, it's a bit complicated to state it, but let's say we have A inside G, so we have an element A inside G, and so there exists an inverse element A to the minus 1 in G such that if we have the product between A and its inverse, we would get this identity element. So, okay, let me use the rotating analogy again to do this. So, let's say we have an action A, or an element A on this thing. So, we can think of that A as a symmetry that leaves it something. So, ignore these prongs on top and think of this as a flat rectangle. All right. So let's rotate it like this. It does nothing to it. It looks exactly the same. That's A. Okay. We rotate it by a symmetry. That's A. So the symmetric line over here is the symmetry, where it looks exactly the same as its mirror image. So if we were to do the inverse, okay, let's do it here, and then we do the inverse by rotating it back. Okay, so we rotate it to the right, and then to do the inverse, we do the opposite of that. We rotate it to the left to do that. Okay, so back to the beginning, right, and then left. It's as if we started, it's as if we did nothing to it, right? The identity element really tells us that we've done nothing to the object. So multiplying this identity element, or applying the identity element to an object. So if we think of the identity element as a rotation on the object, it does nothing. And so those are the three main axioms that a group has to follow in order to be classified as a group. Now, as I said about the ordered pair notation here, over here, or over here, this is the usual way people are introduced to what groups really are. So they're not just a set per se, but rather they are a set with an operation. But we mathematicians, we abuse notation and simply denote it as the set's letter, uppercase letter. So we're saying that this group G is composed of an underlying set N, where an N can contain any object you want. Even if it just has the null set, then that's sufficient, even though it's just a null set. And this operation, null set times null set, gives us null set, or something like that. A null set can also be a group, but I prefer to actually have the set have substance, so that we have something to sort of work with to prove that it actually is a group. So no non-empty sets. So we just use this, and we just abuse notation a bit, just so that it's not cumbersome. So in short, that is what a group is. And there are many things that groups can apply to, such as, well, what I talked about, symmetries, basically lines such that if we rotate the object around it, supposedly to get its mirror image, we'd get just the exact same thing. And also rotation, it also applies in many fields such as physics, supersymmetries, and two-state systems like spin and, matrices actually. Matrices. Sets of matrices can be thought of as groups. And so, actually, that's what a group is. Just a small clarification. This is what a group is. Not just a set, but a set with an operation.